Good evening. Thank you for coming tonight. Um, this is my presentation over COVID-19, modeling it with the SRI model. So, the SIR model stands for susceptible, infected, and recovered. This models a population with a disease. So susceptible is the total number of people who are susceptible to the disease over a period of time. The infected is the total number of people who are infected over a period of time, and recovered is the total number of people who are recovered over a period of time. And if we add these up, with this equation, if we add these up, we can get the total population. So, in order to properly model this, we have to add some parameters. Now, parameters are different from variables and constants. A constant, we can think of a constant, for example, gravity. Gravity is a constant, which is 9.8 meters per second. A variable changes over time. It's dependent on the time. A parameter does not change within the system, but it does change on the situation. So our parameters here we're going to call them beta and alpha. Beta represents the rate of people who become infected, the rate of susceptible people who become infected, and alpha is the rate of the infected people who become recovered. So we can put this into into a system of three equations. Right here, we can see that the total number of susceptible people will only decrease. In this model, it will only decrease. So you will subtract the rate of people who are becoming infected. The rate of people who are becoming infected is any of these people subtracting the people who are becoming recovered. So alpha times I. And the recovered people is the number of infected people who are recovered. I put this into Maple software and I modeled it using that, using arbitrary values for our parameters. So we start with 99% of our population susceptible and 1% infected, with 0.2% infection rate and a 1% recovery rate. And you can see, I probably should have wrote this, but yellow represents the population of susceptible, the green represents the population of recovered, and the red is the infected. So you can see our susceptible start up here and then slowly decrease over time. And this is in days, so this will be over 100 days. Now, there are a lot of assumptions using this model. For one, we're assuming that they become fully immune to this disease after they've been infected, which doesn't represent every disease. And we'll talk about that regarding COVID-19 in a bit. We also assume that nothing else is affecting the population right now. So the only thing affecting the population is this disease. We don't take into account birth rates or death rates. We also assume we're also clumping together the people who are recovered and the people who have died. Any question? Oh. So we can do better with these assumptions. For example, with the SIRS model, which stands for susceptible, infected, recovered, and susceptible. So we add a parameter E, which represents the total number of people who have become susceptible again. So for this model, we can assume that this disease does not make you fully immune after you've been infected, which more accurately represents COVID-19 and other diseases. For example, measles, I believe, you don't become immune after you've become infected. So we use epsilon to represent this, just an arbitrary letter. And so you can add the total number of people who have become recovered again, and then subtract it from the infected population. Yeah. And here I try to match this more accordingly to data I found on COVID-19, to graphs I found on COVID-19. So it showed that COVID was supposed to peak at around 77 days, which is close, but this shows a better, a more accurate representation of how COVID-19 is spreading through our population. It shows a more oscillatory pattern. Now, what if we could do better though? What if we could make this match even more the real data of COVID-19? Well, we can. So I talked about earlier about birth and death rates. Well, these can be called vital dynamics. So U will represent the rate of births, and V will represent the rate of deaths. So putting that into our equations, we can add the number of births and subtract the number of deaths from infected. This way we get an even more oscillatory pattern and an even more accurate representation of how COVID-19 is spreading through our population. And this is over a period of 115 days, so that you could better see how it's waving through. So, this is a graph I found, an image I found from the Business Insider. They got this data April 3rd, so just a few days ago, and they got it from, the data is from Johns Hopkins University. And we can see that it kind of matches right there. See how it's like waving kind of, and that's kind of wavy. So, questions?
I actually did have a question. So your model concerning the sort of situation that would be in, was it based off of those who are also immunocompromised, and would it also include like elderly, or are we going based off of like the average adult human being?
It does not include those parameters, no. Yeah. It would only include the ones we talked about. So, becoming susceptible again, and then how birth and death rates will also affect our population. But I did not consider the immunocompromised, like you stated, so like elderly and people who are younger. And it does not take into account like how being more health conscious affects our data, which it does a lot. If you want to know more about that though, there's a video by 3 Blue 1 Brown on YouTube that can explain that. Any other questions?
Well, I hope this isn't a silly question, but when you talk about the populations that's susceptible, what does that mean exactly?
Well, in a perfect system, everybody is susceptible. That means everybody can contract the disease. Nobody is immune to this disease. So in this, that's another assumption we made, that all, like, excluding the person who's the population that's already been infected, everybody is susceptible to getting this disease.
So they would all be equally susceptible, like no one would have more chance of getting it over another person, right?
Right. Mm-hmm.
Did you encounter discrepancies in the data that you found in your research?
Discrepancies?
Like, yes, did you find different data in different places that you searched for information about the?
That's a good question. So, doing a lot of research, I found that a lot of different people modeled it different ways. So you can look at the whole world, how it's traveling through the whole world, or you can get as small as to how it's traveling through the county. And I didn't go into a lot of research how that data matched, but I'm assuming that they all got their information from one source, which would be the health organization.
You have your total population as one. Could you like scale that to the United States population just by multiplying how many people are in the United States?
Yeah, well, one actually represents a percentage, so 100%.
Right. Okay.
And all of our parameters represent a percentage. So, yeah, so I could model it to the whole population of like the U.S.
Thank you.
You're welcome.